Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on December 31st, 2025, just 2 days ago. It introduces a hierarchical framework that shifts computation from simple tokens to compressed concepts, achieving about a 2.7% improvement across 12 zero-shot benchmarks under matched inference flops. The paper is titled Dynamic Large Concept Models, Latent Reasoning in an Adaptive Semantic Space. And, as we'll see later, the way it disentangles token-level capacity from reasoning capacity is really clever. Figure 1 breaks down how the model turns text into abstract units. On the left, panel B shows the boundary detection, where the model inserts red vertical lines into the sentence. The cat sat on the mat whenever local similarity drops below a threshold. Tokens inside these boundaries are then averaged into single concept vectors, labeled C1 through C4. Moving to panel C on the right, the decoder reconstructs the original sequence. It does this by letting token-level queries attend to these compressed concept keys and values, strictly following the causal mask shown on the far right to prevent looking ahead. So, panel A puts all these pieces together into the full pipeline. On the left, the input tokens first go through the blue encoder and are grouped into concepts shown in the green boxes as C1 through C4. These compressed units then feed into the orange concept model, which performs the heavy thinking, or high-level reasoning. Finally, the purple decoder on the right combines these reasoned concepts with the original fine-grained token details, carried by that blue dashed line at the bottom, to generate the final output text. Well, Figure 1 outlined the architecture, but Figure 2 addresses a major implementation hurdle, the mismatch between token and concept sequence lengths. On the left, we see the problem of variable segments. Since multiple tokens, like T2 and T3, map to a single concept C2, the attention mask develops an irregular, jagged boundary, shown here in red. To fix this, the right panel introduces the solution, called regular alignment. By replicating the concept C2 to match the token positions, the model restores a standard triangular causal mask, which allows it to use optimized flash attention kernels. The text at the bottom confirms the impact. This method is 1.26 to 1.7, 3 times faster than using flex attention. So, while the previous figures established the mechanism, Table 1 details the data used to train it. The authors compile a 1 trillion token corpus balanced between general web text and specialized reasoning data. The first 2 rows show that broad language coverage comes from English and Chinese web text, making up 75% of the total. However, the critical piece for learning dynamic boundaries is the remaining 25%, shown in the bottom rows as OpenCoder and MegaMath. By mixing this dense, structured data with verbose prose, the model is forced to adapt its compression rate to drastic changes in information density. Alright, having covered the data, Figure 6 analyzes the resulting efficiency. Panel A on the left identifies the optimal design by plotting efficiency against the backbone proportion, which is the percentage of parameters allocated to the concept model. The red curve for a compression ratio of 4 peaks around 60%, meaning the model works best when most capacity is shifted to reasoning. Panel B on the right then shows the payoff. As the model size grows along the x-axis, the compute savings climb steeply, reaching over 40% for a 1.3 billion parameter model at the red dot. Okay, Figure 6 promised efficiency, and now Table 2 delivers the performance verdict. Here, the authors compare their dynamic large concept model against a standard llama baseline across 12 zero-shot benchmarks. The top section reveals the model's strength. On reasoning-heavy tasks like OpenBook QA and ARC Easy, we see significant green numbers, with gains reaching 3%. This supports the theory that compressing tokens into concepts helps with high-level logic. However, the middle section shows some red, specifically on text understanding tasks like Bool Q, where the model drops slightly, likely because the compression smooths over fine-grained details. Still, looking at the bottom row, the overall trade-off pays off, with a net average improvement of 2.7%. Wrapping up, 2 takeaways stand out. Effective reasoning does not require uniform token-level granularity, and shifting compute to latent concepts significantly boosts efficiency. This suggests the next generation of models might move beyond surface tokens to adaptive semantic spaces. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.